Hey y'all, welcome back. In this video, I just want to chat about some of the concepts that we've been talking about for the last couple of days, in particular linear and exponential growth. We've learned about both of these as different ways to model change, and I want us to get some practice looking at some problems that do exhibit forms of change and identifying whether it's using linear growth, exponential growth, or something that's neither of those. Okay. So we've talked about both of these forms of change. Let's remind ourselves what the key qualities of each of these are. Right? If you're dealing with linear change, that means that every time you move forward one period of, say, time, or move x up by 1, right, your y quantity is going to change by the same amount. Right? So for example, if you are working a job in Massachusetts, and you're getting $12 an hour, right? That is going to be a linear rate of change, because every time you go forward 1 hour, work 1 more hour, you get $12, right? Remember that these have form y equals mx plus b, where m is that rate of change, how much you are gaining or losing in every time period, and b is your starting quantity, or your y-intercept. Okay. Remember that x might be expressed as t, right, if time is your independent variable. Okay. You might also have exponential change, right? So the idea here is, instead of moving forward by a fixed number each time, you are advancing your y quantity by a fixed percent. Right? So for example, if every year your rent increases by 9%, right, then you're not going to be, your rent is not going to be increasing by a fixed amount each year. You're going to take your previous rent, right, and then add 9% of that, of what your rent originally was, right, and that will determine how much more you gain, right. Remember, our starting quantity, right, is a in the equation for exponential change, a being what we will begin with. B is going to be 1 plus or minus our growth rate or decay rate, right? So if you are increasing by 9% each year, your rent, then this is going to be 1.09, and then raised to the t, right? Basically how many time periods you are going forward, okay? So the big kind of takeaway here is that for linear change, we are just adding or subtracting a fixed number every time. For exponential change, it really matters what quantity we had in the previous time period, right? Because that's going to determine how much we lose or gain in the following time period. Okay, so I want to look at two kinds of problems you might see. One is going to be one where you are actually given some data and are trying to figure out what kind of change you're looking at, and then we'll look at some word problems. Okay, so consider the following functions. For each function, determine if it's linear, exponential, or neither. If it is linear or exponential, write an equation. Right? So the way these work is that we've got functions f, g, h, I, j, right? And then this table is tracking what quantity f, say, is at period 0, 1, 2, 3, right? So it goes from 3.213 to 4.833, and so on. So what I'd like y'all to do on the form is try this on your own, just f and g. Right? Look and see, is f linear, is it exponential, is it neither? If it's linear or exponential, tell me which one it is, and then write an equation representing that change. Okay. So pause and do that. Okay, let's start with f. Right? First question is, does f represent linear growth? Right? We are interested, we don't know if it's linear or exponential, and the easiest thing to do here is to take these piece by piece. Start with saying, is this linear? If it's not, move on to, is this exponential? If it's not that, then it's going to be neither. Okay, so is this linear growth? Right? Well, if it is linear, we would expect our quantity to increase by the same amount each period, right? This clearly is growth, right? If it's linear growth, then we would expect the jump from here to here to be the same as the jump from here to here, adding the same quantity each time. Well, let's check each of these jumps. Right, from period 0 to 1, we gain 1.62. I got that by subtracting the 4.833 minus the first quantity. For the second jump, also 1.62. That's a good sign for linear. For the next jump, 1.62. Each time we go up one time period, we go up 1.62 for our f quantity. Okay? And if we kept on going, we would see that each of these jumps is about 1.62. Okay? So this is looking like linear growth. Right? And so, of course, we don't really need to check exponential. We are done with identifying what kind of growth it is. But we would like to have a formula here. Right? So two things to identify: what's the slope? And if you've already done this check from for each of these between period measurements, the slope is already here. You've discovered that every time you go up one time period, you go up quantity 1.62. So that's actually going to be your slope. That's what you change by every time. And then your y-intercept, it's just going to be your starting value. We started at 3.213. Okay. So y equals mx plus b, right? Or y equals mt plus b here, because t is our independent variable. 1.62, our slope, t, plus our starting value. Okay, here is our formula. For g, right, does this represent linear growth? Right? Well, if it does, we would expect our quantity to increase by the same amount each period. So we'll do the same check that we did for f. Right? Let's go period 0 to 1. Right? We subtract this number, this number from this number. Right? That's a jump of 0.384. Right? That alone, though, is not enough for us to identify whether it's linear or exponential. We need to look at the next jump. From period 1 to 2, that's a jump of 0.442. We don't need to keep checking here, right? That's a pretty different jump, right? Different enough for us to say, this probably isn't linear, right? So next step, let's see if this is exponential growth. If it is exponential growth, then we would expect our quantity to increase by the same percent each period. And to figure out what that percent is, right, we need to use our usual new over old minus 1 formula, right? Where if I'm trying to figure out what the percent change from here to here is, well, here's my new, here's my old, right? If I use this formula, I can figure out what the percent change was from here to here, right? So let's do that. From 0 to 1, new over old minus 1 gives us a 15% increase. If I do the same thing for 1 to 2, now this is my old and this is my new, right? That's a 15% increase. 2 to 3, 15% increase. And I could keep going, and each time it's going to be about a 15% increase. So this is looking like exponential growth. If we wanted to write a formula for this, we need two things. We need the starting value, which is going to be 2.56. And then we need the growth rate, right? So remember, b is 1 plus or minus our growth rate, right? And here, growth rate is positive, so our growth rate will be 1, the b will be 1.15 raised to the t. Okay, and there's our formula. Okay, you might also see these kind of questions in the form of a word problem. Right, so here's one. My car is currently worth $16,000. Its value decreases by $2,300 each year. Excuse me. When will it be worth $5,000? Okay, first question. Well, first of all, y'all try this on your own, right? And then we'll step through it. First, same question as we had for looking at f and g and trying to figure out, are those linear exponential functions? Is this linear, right? This is clearly decline, right? You bought your car and it's depreciating over time in its value, right? If it's linear decline, we would expect our quantity to decrease by the same amount each period, right? Now, if you want, you can write out the values, what the value of the car after each year, and then subtract during each period, just like we did for the previous problem. That's more work than you need to do, though, right? To identify this as linear change, you just have to basically read the problem, right? Its value decreases by 2,300 each year, right? This 2,300 amount drop is fixed. It's not contingent upon the current value of the car, right? In order to figure out what the price decrease is, I don't need to know that it's time period 3 or 4 or what my current price of the car is, right? If it was exponential decay, I would need to know that, right? But here, I know that the change is always going to be 2,300, so this is going to be linear decline. Let's write the formula. Slope is negative 2,300, right? Because it's dropping by 2,300 each year. Starting value when you bought it was, or when you had it initially, was 16,000. So plugging those in, here's our formula. Now, that wasn't actually what they asked us here. When will it be worth 5,000? Well, that's going to be a y value, right? We want to plug that on the left-hand side, right? Because that wouldn't make sense to plug in for time, right? And if we do that, we can solve for t here to be 4.78. So for about 4.78 years, just under 5 years, your car will be worth $5,000. Sorry, that was my alarm. So that was an exponential decrease. Let's have a look at one that is maybe exponential. Spoilers. So white bread cost 90 cents per pound last year and 92 cents per pound this year. The price continues to rise by the same percentage each year. Write an equation for the cost of bread. How much will it cost in 10 years? So again, try your hand at this, right? See what kind of growth it is, right? And try to write an equation for it and try to make this prediction for 10 years from now. Okay, and there is bread in case you forgot what that looks like. Same starting question. Is this linear growth? It's clearly growth because the bread is getting more expensive every year. To be linear growth, we would need for the bread to go up by the same price, by the same amount of dollars or fraction of a dollar every year. Right? We can tell that this is not linear growth because the price is growing by the same percentage each year. What that means is that it's not going to go up by 2 cents every year, right? This 2 cents was instead calculated by taking a percent of this 90 cents, right, and adding that to itself. Right? So when I'm trying to get the price after the 92 cents year, 92 cents a year, I'm going to take a similar percent of 92 cents and add that to the 92 cents. Okay? So it's not going to be the same fixed amount every time. Right? So this can't be linear growth. Rather, it's going to be exponential growth. Okay, so now that we've acknowledge that it's going to be exponential growth, right? Let's write the formula. We need two things. We need the starting value, which was 92 cents. Be careful here. It's tempting to say 90 cents, right? Remember that 90 cents is the cost of bread last year, right? So if you're trying to write a function or an equation which represents how much the bread will cost in so many years from now, right? You want to start with 92 cents because that's how much bread costs right now. Right, in time period 0. The percent change, right, new over old minus 1, right, is going to be a 2.22% growth, right? If I wanted to plug that in for B, it's 1 plus 0.0222, right? And this would be our final formula. Now, the question is, how much will it cost in 10 years? Let's just plug in 10 into T. And that should get us $1.15 per pound in 10 years. Okay. Soon we will, I think later this coming week, we'll talk about how to, if I asked you, say, when will the bread cost $2, right? Plug in y equals 2. We'll talk about how to solve that kind of equation later this week. Okay, last problem, right? You love Snickers. Okay? Your friend gets you a giant one for your birthday. It's 36 inches long. You eat 3 inches off the giant Snickers bar every day. When there are only 12 inches left, you start only eating 20% of the remaining candy every day because it's so good and you don't want it to be gone. 2 questions for you. If you continue eating in this manner, will you ever finish the Snickers bar? And after 20 days, how many inches of the Snickers bar will remain? Okay, so take a second, answer those on the form. This will be the last couple of questions here. Okay, so first of all, what kind of decay is this? Clearly we are losing pieces of the Snickers every day, so it's some kind of decay. Is it linear or exponential? And the answer is here, both. Right? Initially, it's going to be linear, right? Because you are biting off the same amount every day. You're losing the same quantity of the Snickers bar, right? And then when there's 12 inches left, it becomes exponential decay, right? You start eating less and less of it every day, right? You eat 20% of it every day. But because the Snickers bar is getting shorter and shorter, that 20% represents less and less of the remaining Snickers bar, so that you're taking basically a smaller and smaller bite out of it every day. Okay. So now let's answer the first question. If you continue eating in this manner, will you ever finish the Snickers bar? Right? Well, let's say that you actually do get to the point where there's 12 inches left on the bar. You've been eating 3 inches a day, but now there's only a foot left, right? 12 inches left. You eat 20% of what's left every day from then on. So initially you have 12 inches. Then the next day you eat 20% of that, right? You're down to 9.6 inches. Then you eat 20% of that, you're down to 7.68 inches and 6.144. Right? If you get down to, say, day 100, this is how many inches of Snickers you have left. Right? If we keep on taking off 20%, right, we're actually never going to get to 0. Right? So you'll never, if you were to keep on doing this, right, which I think you'd probably get tired of it eventually, but if theoretically you kept on doing it, right, you would never actually get to the end of the Snickers bar. Okay? So answer to this, no, right? You don't hit 0 with exponential decay. You can hit it with linear decay, but since the latter part of this change is exponential, you're actually never going to quite get to the end of the Snickers bar if you continue in this manner. Okay. Second question, after 20 days, how many inches of the Snickers bar will remain? In order to answer this, we need to consider first the linear decrease and then the exponential decay, right? Because there's 2 parts to this eating habit you've developed of the Snickers bar. Okay? Let's start with the linear decrease. Every day, you're going to chomp off 3 inches from the Snickers bar. Right? So if we're trying to write some kind of linear decrease equation, right, that means that m is -3. You're losing 3 inches every day. You started with 36 inches, so b is going to be 36. Right? If you were to make an equation for these first few days of you munching on the Snickers bar, would be y is -3t plus 36. You switch to exponential decay when there's 12 inches left, right? So I need to know basically how many days did you spend in this first linear decrease phase, right? So if we plug in 12 into the left-hand side of our equation, right, basically asking how long did it take us to get down to 12 inches and solve for t, that'll tell us how many days it took us to get down to 12 inches. And of course, that is the start of our exponential decay after that, right? So let's say this first 8 days. Remember that the first phase of this lasted 8 days, right? And then we need to figure out, okay, we spent 8 days munching on this linearly. And then when we got to 12 inches left, right, that means that I need to figure out, okay, what about the remainder of the 20 days, right? We've spent 8 already. Now I'm going to be chomping on this the Snickers bar in an exponential decay fashion for 12 days, right? Because it was 20 days, I've spent 8 already, there's 12 left. Right? So in other words, if I start with a Snickers bar that's 12 inches long and I chomp off 20% every day for 12 days, how much is left? That's the problem that faces us now. Right? We need to figure what this looks like in our exponential formula. Right? Our current bar quantity is 12 inches, right? I know that originally it was 36, but at this stage of the problem, where we're dealing with exponential decay, you're actually starting with 12 inches because that's what's left at that point. Right? Percent change is a 20% decrease, right? And that's clearly not right. There we go. Right. 1 minus 0.2 is going to be an 80%. It's basically our b is going to be 80%. Basically, every time we multiply by b, we're going to be taking 80% of the quantity we had last period, right? That is losing 20% of it. Right? And if we plug 12 into our equation here, we should get that after 20 days, right, our Snickers bar has gotten down to 0.82 inches. Okay, and that's the last problem that combined both linear and exponential decay. right? And if that one made sense to you, you should be in pretty good shape going forward on this. Let me know if you have any questions on this video. Finish filling out the form, and I will see y'all in the next one.